So welcome everyone. Today we have Professor Bhavin Shastri from Queen's University in Kingston in Canada. He has received his PhD in electrical engineering from McGill, working on photonics, and then spent some time in Princeton doing a postdoctoral fellowship in Princeton before coming back to Kingston in Queen University. And today is going to talk about neuromorphic photonics for neuromorphic computing, and we'll explain a little bit also the history of the field of photonics and this application to AI. So without further ado, like Bhavin, please give it up. Give it away.
Um, thank you. Thank you very much. I'm sharing my screen. Is that coming okay?
Yeah.
All right. So thank you very much for the introduction, and also thank you for having me here today. Today I'll be talking about uh, how we are interested in implementing neural networks in photonic hardware, and specifically in silicon photonics, and how that can potentially enable new class of applications in artificial intelligence and neuromorphic computing. So I'm an assistant professor at Queen's University in Canada. I'm affiliated with the Vector Institute for AI in Toronto. And a lot of this work that I'll be presenting started off in Professor Paul Prusmel's lab at Princeton, where I was there as a postdoc for several years. So a lot of this is also joint work. And I would also like to acknowledge our collaborators whose work that I'll also be including in today's presentation. I would also like to give a shout out to the fabrication support that we get here in Canada through the Canadian Microelectronics Corporation, the SciPic Fab Consortium, and also Applied Nanotools, where we fabricate a lot of our chips, and also through multi-project wafer runs and in Singapore at the Advanced Microfoundry. Of course, I would like to acknowledge our students. Really, the work that I'll be presenting is, it's all done by them. And so I'm just here as a spokesperson for the work that they have done. And I'm just glad that I get this opportunity to present their work, both from students in my group and also students in Professor Paul Prusmel's lab, with whom we collaborate very closely. So here is an outline of my presentation. I'll start off with a brief introduction and talk about why we are interested in using neural network hardware for applications in AI and neuromorphic computing, and specifically talk about why photonics might be a good platform. But what are the challenges? I'll give a bit of perspective as to where we have come from and what has been the recent work that's gone in neuromorphic photonics. I will then talk about how we can implement these neural networks in photonic hardware, especially using silicon photonics, and take more of a tutorial type of approach where I show sort of step by step how we're building this hardware, and then highlight a few applications depending on the interest of time, and then leave discussions open. But please feel free, to ask me questions as we go along. I will be stopping at specific points, and so at that point you can ask me questions. So we know AI is all around us right now. There are a number of applications, from natural language processing to drug discovery, to in the medical field, and so on and so forth. And a lot of these applications, the machines have approached or even exceeded human level accuracy. So, AI is not a new field. It's been around for 60 years. But what has really enabled AI over the last decade or so has been some of the very interesting work that started at the University of Toronto here in Canada, done by Jeff Hinton and also Yoshua Bengio. And this is essentially trying to implement this AI that is enabled by what are called deep neural networks. So here's just a schematic of what a deep neural network might look like. You have multiple layers. Each layer has got neurons, and And the data with the way this processes in neural network is essentially using linear algebra. So you can imagine some input that is put into this network. It can be vectorized. And so you have this, the first layer, you'd essentially have some, some vector that are put into the first layer. And that vector is then multiplied by a matrix, which is essentially what's called a weight matrix, which is a connection between one set of neurons to the other set of neurons that can be represented by a matrix. So the resulting vector matrix multiply essentially gives you another vector that is then processed by the next layer, and so on and so forth. And each layer does a unique task. And in the end, you can do some classification, based on the features that you might have extracted. And so the point here is that, whether you're doing inference or what's also called training of these networks, for example, backpropagation, you spend a lot of time doing this vector matrix or multiplication, which is essentially linear algebra. But also the movement of data to and from memory takes a lot of resources, essentially loading and reloading the weights. And so there's a big computational cost that you have to pay, right? So if you can imagine that over the years, this deep neural network performance has been improving, but this is really coming at the cost of the computational power, which is really measured in operations per second. And if I was to measure this computational power over the last, 60 years, you see that there are two distinct errors that have happened. So there's the first error where this computational power was doubling every 2 years or so. So this y-axis is on a log scale. And this was fine because the computers were also getting better. They were improving. The performance was doubling every 2 years. But over the last 10 years, the applications have demanded much higher computational power. For example, you have AlphaGo, which is essentially the system that was used to train to play Go and beat a human world champion, required close to 2,000 CPUs and hundreds of GPUs just working in unison to harness that computational power. So this computational power that's required now to train this AI systems is doubling every 3.5 months. So even if Moore's law were to keep up, for example, where the computational power keeps doubling every 2 years, we just see that current hardware is not, is not sustainable. And not to mention all the energy costs, right? So if you're using all this computational power, you're really generating a lot of heat. You need to cool it up. There's a carbon footprint that you need to pay. So there's also, if you look at it from an energy perspective, there's a big motivation to reduce the carbon footprint as well. So the challenge is because of the current computing platforms that we are using, right, which is all based on what's called the standard von Neumann architecture, where you have a separate memory and a separate processor. And this is very good for sequential-based type of programs. For digital logic, which is all procedure-based, you do A, B, C, D in that sequence. But neural networks, things are happening in parallel. If this is distributed, it's massively adaptive. And so in this case, you need to have very tight co-integration of memory and processor, and von Neumann machines are very inefficient at that. Now, having mentioned that, there's been lots of work on hardware-based accelerators where people have tried to improve the performance, to do this, what are called tensor-based based units to implement this multiply accumulate operations, or this vector matrix multipliers essentially. And they've been able to get some impressive performances. These are different graphics cards like NVIDIA GPU, the Google's tensor processing unit, and also specialized ASICs. Question is, what comes next? What comes, and can we do better? So to kind of summarize, today neural networks are kind of implemented in software on digital hardware. This digital hardware is based on some type of transistors where you make gates and then registers, and then you implement some type of vector matrix multipliers. And while it's not a very natural way of doing things, you can still do that. And there are a number of applications that we see already today, for example, in speech recognition, object recognition, sort of on the hertz to kilohertz timescales. On the other hand, we have what we can do is implement this neural networks in hardware. And this is what's called neuromorphic engineering, where we're really trying to use the physics of our platform to implement this type of, to implement the biophysics of neurons. And hence we can potentially get real-time processing and also do this on with little energy. And this is a paper that was published in Nature, I think back in 1980s or 1990s by Misha Mahawal, right? And so clearly there's been motivation in this area for a very long time. Currently, there's been a lot of work done by lots of companies like Intel, IBM, HP. We're trying to implement this type of neuromorphic hardware using various types of architectures. But the challenge here is the interconnects, right? So if you want to start making large-scale neural networks, you need to connect many neurons with many neurons. So when one neuron is connected by many neurons, this is called fan-in or fan-out. And physically, if you start bringing in many wires together, we start limiting the bandwidth because we have capacitive loading, electromagnetic interference, and not to mention all the topological constraints. So this limits the bandwidth. So there's this trade-off between bandwidth and complexity. And so, there are impressive applications that have been demonstrated, sort of like real-time image and video processing. But this is on the kilohertz, the megahertz sort of time scales. I come from the optics background, and so what we are very interested is in pushing that type of processing on the picosecond time scale, in gigahertz processing speeds. So the question is, can we enable a new class of applications that might be very challenging for electronics? We don't want to target the same applications that electronics is already very good at, but look at what are the new applications that we can potentially enable. And I'll talk about this in just a bit. So, when we start talking about doing any type of computing with optics, I'm kind of reminded about some of these criticisms that were laid out by Robert Keyes. He talked about why optics is not very good for doing computing. And there are some very nice papers that he had here in the 1980s that I've highlighted here. And here were his concerns, right? So number one is, for any type of processing, we need to have things like nonlinearity, memory, gain. We need to communicate that information. We need to do some type of linear algebra. And then are we going to go from optics to electronics and so on and so forth? So with electronics, if we were to just kind of put this in a table format, we realize that doing things like nonlinearity, memory, and gain is so easy in electronics. But you do pay a cost in terms of doing some type of communication or fan out, as I highlighted a bit earlier, because you have transmission lines and they are capacitive in nature. So fundamentally you need to overcome that capacitance and you need to pay an energy cost. Linear algebra, is surprisingly hard in digital electronics, right? It's not something that happens very, very naturally. And I'll come to the domain crossing in just a second. But if you look at photonics, the inverse is true, right? Implementing things like nonlinearities is very difficult. Memory is very hard. Gain is potentially easy now, but and I'll also talk about that. But communication and fan out is essentially free. We have waveguides that have essentially no inductance at all, and so communicating information, you're really paying no energy cost apart from converting from electronics to optics. And doing things like linear algebra is very easy because of linear optics, and that's what it's really meant for. You can do this, in principle, with zero energy linear algebra. And you can also now go from the, what's called OEO here. You can go from the optics to electronics back to the optics domain. And people have now shown that you can implement things like memory, and also that I'll talk about that you can implement things like nonlinearity. And so I'll talk about a bit more in details, but this is kind of, if you want to take a first pass at how electronics and photonics compare in a table format, this is essentially how I'll put it. The question is, have we been here before, and what has changed? So there's some very interesting work done by Dimitri Psaltis back at Caltech back in the 1980s. I was just talking to Gert just before this presentation, and so where he recognized that you can make neural networks with optics, and again, why we want to use optics for doing neural networks, that has not changed, right? So even in this paper here, he showed that you can have this massive number of interconnects. You can do a lot of this parallel processing here. In fact, he showed 10 to the 6 parallel interconnects, 10 to the 6 parallel processing. But if you see here, the nonlinearity is implemented, it's not done in it's not done in optics. This is implemented in electronics. And also this were large free space type of optical neural networks using tens of meters of square meters of space. So clearly, that would limit the application potential. Now, what's happened over the last several years is that we have the rise in photonic integration technologies. People have found that you can miniaturize a lot of these optical components and now put them on a chip. This is done using, you can now integrate lasers, you can integrate waveguides, essentially fibers now, what are called waveguides on chip. You can integrate a whole slew of optical components. And the number of optical components that you can integrate is now increasing. It's essentially climbing up like a Moore's law-like trend. And one area that has really garnered a lot of momentum is called silicon photonics. So using that platform, which I'll be talking about just very briefly, we've been able to start implementing these neural networks in photonic hardware using these advances in silicon photonics, and now showing a whole new class of applications, And what are those applications? For example, things like nonlinear programming, where you might want to solve optimization problems. Here's a project that we had with in collaboration with Lockheed Martin that was funded by DARPA, where we wanted to predict where an object is going to be in the future. And so you're trying to predict where something is going to be in the future by looking at current events, and that boils down to solving an optimization problem. And what we showed in this paper is that you can actually use a photonic integrated circuit and solve these optimization problems on a nanosecond time scale. This was really inspired by the work done by John Hopfield and David Tank 30 years ago. You can solve ordinary differential equations, also partial differential equations, using photonic neural networks, and do this on a much, much faster time scale. We proposed this in a paper just a few years earlier. There's been lots of work in trying to speed up this vector matrix multipliers. There's a paper that came out by MIT, by Dirk England and Marian Soljacic's group a few years ago that was published, where they showed that you can actually do this in principle with very little energy. I'll be talking a bit about this today, but we can actually also do intelligent signal processing of optical signals, which are already in the analog domain, and you need very, very low latency. You can also process wireless signals where these are already in the analog domain and they're very high bandwidth. So you, again, using optical neural networks, this is again, where latency becomes very important. And then there are numerous other applications that people are starting to look into. For example, in detecting particles, looking at interesting collisions that are happening in particle physics experiments, and also in quantum tomography, in real time, trying to adjust this quantum-based systems, and using predictive-based algorithms. So having said that, highlighted a number of these applications, this is just showing now, what are the different types of photonic architectures. So there's been lots of work on what's called reservoir computing. I'm sorry, I don't know why the C is not showing up here, but there's been lots of work that's going on in Europe in trying to do reservoir computing that I'll talk about very briefly. And apparently, photonics is a very good platform for doing that. We've worked on what are called multi-wavelength optical neural networks, where we can do a lot of large-scale processing using multiple wavelengths of light. And so we can get this massive parallel processing that I'll be talking about today. So we have had a number of papers that have come out in this area, and also there's a very nice paper that just came out in Nature earlier this year by Bhaskaran's group at Oxford. There's been approaches where you can use coherent-based type of schemes where you're using a single wavelength of light, but you can actually implement matrix multipliers here. And I'll talk about this also briefly. You can also implement other types of neural networks, for example, spiking-based neural networks, using and looking at really at the dynamics of lasers and resonators, and showing that the physics of these lasers is very much tied with the with the integrated fire models of neurons. And so we've done a lot of work in this area as well. There's been lots of work on using diffractive optics, and also people trying to implement neural networks in superconducting hardware in optoelectronics, and these are for a whole new other class of applications. So to highlight a bit, there's been some work on what's called photonic reservoir computing, and the idea here you might have heard about reservoir computing, but here, what a reservoir essentially is, this is a concept proposed by Herbert Jaeger and Wolfgang Mass, almost 20 years ago, where they said, you can have this collection of neurons. And this neurons, what we'll do is that we'll just assign them random but fixed weights from the inputs to this reservoir, and then we'll only train the output layer. And the reason for doing this is essentially increasing the number of dimensions that you can have, right? So imagine if you have this plot here at the bottom left, and you want to linearly separate these two orange stars from the two yellow balls in the X and Y plane, it's very difficult to do so. They're not linearly separable. But by increasing the number of dimensions here, you can then potentially separate them linearly using this hyperplane. So this reservoir computing approach is very interesting because it allows you to, go to higher and higher dimensions, and that makes the classification very easier. Well, why is optics very good for that? Well, it's good because you can implement this using very minimal hardware. What was shown here by Laurent Lager at FemtoST and also Daniel Brunner back, almost again 20 years ago, you can just use a single laser and a fiber, just a fiber optic cable, and you can connect this in a feedback fashion, and you can create what are called virtual nodes. So by doing this and using time multiplexing, because optics is really fast, you have this light going around this fiber on essentially, on a nanosecond time scale, and you can do this processing very, very fast. And they were able to show this, that you can do things like, spoken digit classification, time series prediction using 5 gigahertz bandwidth, and get very, very low errors, and that too at that time. Another interesting work that has happened is people using what are called Mach-Zehnder interferometers to implement neural networks. So these are called coherent-based networks, and I'll explain what I mean by that. So in what we know is that any matrix N can be decomposed using single value decomposition into a unitary matrix and a diagonal matrix, shown by this expression here. And what is well known in optics, for many, many years, is that you can, in fact, implement a unitary transform using what's called a Mach-Zehnder-based interferometer. So I can have light that's going into this two waveguides. I can couple this light here, and then I can apply this phase shifters. And then I can look at the input and output, and that can be represented by a unitary transform. So the idea here was that now that the fact that I can do this unitary transform, which means I can implement a unitary matrix here. And so I can use this type of Mach-Zehnder interferometer as a building block too, and I can put them in this very interesting configuration as shown here to start implementing, breaking down this matrix here. So in hardware, you have taken this matrix and broken it down into a series of this Mach-Zehnder meshes. And now I put an electromagnetic wave on the side here. And by the time it comes out on the other side, essentially it's matrix multiplied by this value M. So you can imagine that you have your weight matrices implemented in hardware with M. You have your inputs coming in here. And essentially you just multiply your matrix. And this, I'm sorry, my animation is all over the place, but essentially you can do this at the speed at which this electromagnetic wave is going across this chip. In this particular case, of course, the nonlinearity was implemented offline, but this was essentially, a building block for this type of systems. And there's been a lot of work in this area. So we have covered a lot of this integrated technologies. What are the advances in science and technology that would be required to scale up the systems? In an article that came out in Nature Photonics a few months ago. So if you're interested, please check out this paper. There's a very nice historical perspective that came out as a perspective article in Nature. This was by Dimitri Saltis, just late last year. And there's also concurrently another paper that came out on how you can program this photonic integrated circuits that was also published as a review article in Nature late last year. So I think these 3 articles, highlight the recent advances, but also some of the historical perspectives. And now I'll talk about how we can build this type of neural networks in hardware using silicon photonics. So maybe it's a good time. Oh, I have to mention that that while we're doing this in the lab, There have been lots of companies that have started in this area. So there's one that spun out from Princeton called Luminous Computing, and they have been getting a lot of seed funding to build this type of systems. And then there are other companies, for example, Light Matter that spins out from MIT and others. I think Lighton is a company that Sylvain Guigan is associated with in France, and there are several other ones as well. So I'll now talk about how we can implement this neural networks, in photonic hardware. But at this point, are there any questions that I can answer? Okay, if there are no questions, then I'll
actually, I have a quick question.
Yes.
So are all of these methods potentially trainable, or are some of these methods such that you necessarily have to train the weight matrices offline and then embed those into this hardware?
It's a very good question. So the question is, are all of this approaches where the weights are kind of just static and you just have to train the systems offline, or can you kind of train them, in situ? So the answer is yes. The Maxender approach, and even the approach that I'll be talking about using microresonators, people are showing that you can actually train them now in hardware itself. There's been lots of work that's going on in that area. It's very new right now, so there's not much literature. But to answer your question, that just sort of simply that yes, they are trainable. But a lot of this demonstration that I showed on the previous slides, this were with static weights. Yeah.
Great, thanks.
Yeah. Okay. So I'll continue, but if you have any questions, please let me know. So now, how we can actually build a neural network with this. So I'll talk about two things: how we build a neuron, and then how we build a neural network with photonic hardware. So here I'm zooming into one of these neurons. As we see these neurons, what they're doing is that it has inputs that are coming in from previous layer. We're going to represent this as a vector X. And then we have an element-wise multiplication. So we would have this, essentially it's multiplied by this weights. We sum up everything together. And so you can imagine this is essentially doing a dot product of two vectors, X and W. So that's a linear part. And then you have the nonlinear part where you are going to do the decision making. So this is implemented. This is essentially, you need some type of a nonlinearity or nonlinear activation function where you compare it with certain threshold and you let the signal, either go through or not. So we talk about how we build both this, the linearities and the nonlinearities before we talk about the interconnections. So to do this, we look at a very simple, I'll just provide a quick background. What you're seeing here is a top view of a silicon waveguide that's implemented on top of a silicon oxide layer. This is a dimension here, 10 microns. It's a small waveguide, and if you look at the cross section, you can see that this is just a waveguide, silicon waveguide, which has a higher refractive index than the air around it on top of glass or silicon oxide. I can put in an optical mode on one side, on the left-hand side, and I can measure what's coming out on the other side of this chip, which is the through port. And I can plot the transmission. So if this has very little loss, or zero to little loss, I should see essentially all the light that I'm putting on one side of the chip coming out on the other side, regardless of the wavelength of light. So this different numbers here represent frequencies of light or different colors of light. But this should essentially be flat, as long as we are in this infrared region. That's where silicon is transparent. Now, what I want to do is weight the signal, right? So what I end up doing is I put in what is called a resonator or a ring resonator very close to this waveguide. So this is an electromagnetic wave, and some of this light is going to get coupled into this waveguide. And as it gets coupled into the waveguide, it's going to go across a circular loop. It's going to acquire phase shift. This phase shift that it's going to acquire is going to depend on a few things. It's going to depend on the refractive index of this medium that I have. It's going to depend on the radius of the ring and the wavelength of light that I'm injecting by. And so I'm going to acquire a certain phase. Now, if this phase that is acquired If it is an integer multiple of 2 pi, essentially you can think of this as forming a standing wave inside the ring, then it's going to constructively interfere with the light here, with the incoming light. And in doing so, I'm going to start trapping in all the light into this resonator. So this is called at a particular wavelength of light called lambda r. And when that happens, at that particular wavelength, all the light gets trapped into this resonator. And this is shown here in this through port. So I'll otherwise have unity transmission, but at that specific wavelength of light, all the light gets trapped in. And this happens at particular frequencies, and this is repeatable, and this is called the free spectral range of your resonator. And how well you trap the light, this is called the full width half mask, or the quality factor of your ring. Now I can break this resonant condition by putting a drop port at the top here. That's a waveguide on the top of this ring resonator, and that's called the drop port. And by symmetry, I'll have the transmission profile that looks exactly the opposite. Now, what happens if I wanted to change the incoming, if I wanted to change the transmission, if I wanted to move this transmission curve, then I need to change the resonant wavelength. The way I can do this is by changing the refractive index, because the radius of my ring is fixed. So the way I do this is by I deposit a little metal layer on top of this ring, and I input a current. This metal piece has a certain resistance. So if I put in a current, there's going to be power drop across this resistance, and that's going to translate into some temperature. The temperature locally hits the material here. And by heating that material, it changes the material properties, and that affects the refractive index of your silicon. And so essentially what I've shown here is that I can change the current here. And by using what this call is thermo-optic effect, I can change the refractive index of my medium. So if I blow in at the transmission of the drop port here, I can put in a particular frequency of light here, shown here, x as a function of lambda. And I might be getting in all the light that whatever goes in comes out at the drop port. But by putting in this current here, I can weight the signal. So now, if I start heating this, what you see is my transmission profile moving. And now the amount of light that comes out has dropped. So I can think of this essentially as some of my light being weighted by a certain amount, right? And this is happening for one single device. So this is essentially the building block. Now what I can do is I can put multiple frequencies of light with essentially multiple colors of light, modulate different signals on them, multiplex it in a single waveguide, and then I use multiple of these microring resonators that I showed in the previous slide, and each tuned to a specific wavelength of light, and each one of them is weighting the signal. So here I have my first resonator tuned to the red light, and it's weighting this red light. The yellow resonator is weighting the yellow light. And so I can tune each of these resonators by controlling their refractive index, and hence control the amount of light that's going to come out. So I can have all of these operations happening in parallel. So this is where the beauty of wavelength multiplexing comes into play, using different colors of light. And then once I have that, I can sum up everything using a single photodetector. And I'll talk about what this configuration is here. But here you can see that I'm doing essentially a dot product of two vectors that's happening essentially at the speed at which I'm detecting the signals here, which can be very fast, on a picosecond time scale. Now, light is essentially 0 or 1. So the question is, how do we get negative weights? So we use this balanced configuration of this photodetectors as shown here. We have the top photodetector subtracting whatever signal is coming out from the bottom photodetector signal, subtracting whatever current that's coming out from the top photodetector. So this is throughput and dropput that I have here, essentially subtracting the two. So imagine if I wanted a weight of 0.8, what I would do is that I would have my 90% of my signal come on top, 10% of the signal come at the bottom. And by having this balanced configuration, I'd have a resultant electric current that is going to represent a weight of 0.8. Well, what happens if I want a weight of negative 0.8? Then simply what I do is just tune my resonators such that I have 10% of my signal coming out on the top waveguide and 90% coming out on the bottom waveguide, and therefore, by virtue of the subtraction, I get a negative weight. I can then convert that current into a voltage, and that gives me a signal that I can drive a modulator and exploit this electro-optic conversion back into the optical domain on a different frequency of light as shown here. And that is a nonlinear process. And I can exploit this nonlinearity to get my activation functions. So this first part here, I'll just show you some experimental results. We were able to put this, what we call microring resonator weight banks, each one of them tuned to a specific wavelength of light. So this is all experimental results. And now I can tune each of these resonators by controlling the amount of current going to each of these resonators. And whether I put them on the drop port or the through port, depending on whether you have the top photodetector or the bottom photodetector, you can see I can get both positive and negative currents. The question is, I can go any value between 0 here and 1. So I can weight any value between 0 and 1 and also get the negative part, right? So any value between -1 and +1. Question is, what is the resolution can I get? What is the bit precision? So we have come up with what are called weight control methods to control this very precisely. And what we showed a few years ago that we were able to get around 5 bits of precision. In the interest of time, I'm not going to be able to go into the details right now, but happy to answer questions. But what we've been able to show very recently, we have a paper that just went on archive, we have now been able to get 9 bits of precision using very precise control. So that's one way in which we can implement this weights. And then to implement the nonlinearity, we again use this microring resonator. But here, we want this to be very, very fast, right? So we want to be able to modulate the signal very fast. So what we do is that we dope this piece of silicon with a p-type and an n-type material. Why do we do that? Well, we do that because we know about diodes, we know about transistors. And so what we create is what's called a p-n junction in the silicon. Again, it's the same platform that you're making to do electronic circuits. You're using the same platform for optics. So we can dope the silicon with a p-type and n-type material. So we have a majority of charge carriers and majority of holes on one side. And that creates what's called a depletion region, a charge neutral region. And there's pioneering work done by Richard Soref, who showed that there are electro-optic effects in silicon. Particularly what he showed that I can tune the number of free carriers in this piece of silicon, and that would affect my refractive index, shown by this empirical equation here. Not only that, I mentioned, remember that this silicon waveguide is essentially lossless, it's essentially transparent. Well, not anymore. By having this amount of free carriers, I can affect the amount of loss that I have or the amount of attenuation that I have in this waveguide. So I now have this 2 degrees of freedom. I can now change the number of free carriers that I have in this waveguide and affect the refractive index rather than using temperature. And I can affect also the amount of loss that I have. And this happens on a picosecond time scale. And this is what my electric input that's going to come here. It's going to modulate the amount of refractive index that I have. So we fabricated such a device where we have our balanced photodetectors connected to this modulator. And then we can bias this modulator and control the amount of free carrier dispersion, essentially the refractive index, and the amount of loss. And I can then get different types of transfer functions that are shown here. This is all reconfigurable. This is a single device giving you this different types of transfer functions. So you can get sigmoids, inverse reduce, quadratic that can be used in different types of neural networks depending on your application. So we've been able to take this whole resonator weight bank and the nonlinearities and put everything monolithically on the same platform. We can do parallel processing. This is all enabled by using wavelength multiplexing. We can get both positive and negative weights. And we can implement this nonlinearities on chip. And this is all compatible with standard silicon photonic foundries. So this is all fabricated essentially with commercial foundries. This is not what we fabricated even in the lab. So this is scalable. And I'll show on the next slide how this is scalable. The efficiencies that we get today in the lab is around 500 femtojoules per Mach, or for doing a multiply accumulate operation. And people have shown that by getting very, very efficient photodetectors to modulate this OEO conversion, you can get down to around 1.1 femtojoules and potentially attojoules per Mach operations. Essentially, a vector dot product can be done with very, very little energy, with, of course, with very high speeds. Let me now briefly talk about how we're connecting these neurons together. I've shown how we can make a single neuron, but let me show how now we can connect these neurons together. So I'm going to use a shorthand notation here of my neuron. These are my signals coming in X. These are my resonator weight banks represented by W weights. Photodetect everything, and then I have a nonlinearity, and then I put it back on my, I convert it back into optics using with this modulator. So what I can do is now put this modulator on a single waveguide. This is called a broadcast loop, and I can put multiple neurons on this waveguide, right? So I can have this pink neuron and this purple neuron and this blue neuron, all on a single waveguide. What you can see from here is that I'm using just a single waveguide to connect all these N neurons together. I don't have N squared wires. I don't have N wires here. And I can start putting in, multiple neurons, and each neuron just is identified by a frequency of light, by a particular wavelength of light. So this wavelength multiplexing essentially allows us to get all-to-all interconnects. Why is this significant, you might ask? Why is this, why would I be interested in this? Well, the reason you might be interested, and I missed a point here, we have done analysis to show how many neurons you can put on this waveguide, and I'll just skip over this, just in the interest of time, but happy to talk about the scalability of this platform during the discussion. So you might ask, why is this significant? Well, we can create recurrent networks like this. So if you had each neuron connected to every single neuron, you would have essentially N squared interconnects that you would need to connect N neurons together. We can use a single waveguide here and put multiple neurons on this. So you can get N squared connections just with a single waveguide. Because each neuron is identified with a unique wavelength of light, we're not providing addresses or anything like that, the way you would on an electronics platform where you need to provide address headers to each neuron. So here there's no switching, there's no routing that's required. And importantly, here the bandwidth is not limited by the interconnect complexity, right? If I wanted another neuron, I simply just put another neuron on this highway, right? And I don't need to put, while in electronics, what I might need to do, if I need to put one neuron, I need to put N more wires together. While here now, I can just put everything on this essentially this highway, and this can be done very simply. If I wanted to create feed-forward networks, you might ask, well, what I can do is instead of outputting on the same waveguide, I can now output onto another waveguide. And so this is what's shown here. So this is what my neuron would be, but simply I can just output on another waveguide, and then I can stack different broadcast loops that way to create a feed-forward network. If I wanted to create a feed-forward plus a recurrent network that looks something like this, essentially, I can do it in this configuration where I have a broadcast loop with this interfacial neurons, and then I can start creating hierarchical networks and complex systems out of this. So this is what physically it looks like. I showed a lot of cartoons, but this is actual physical implementation. We have in our lab, we create what are called procedural-based layout tools, where we essentially write a lot of this Python libraries and codes that is implemented in Python libraries, and then we can specify what type of neural networks that we want, and we can generate this type of layout. So this is a chip that is an 8x3 millimeter silicon photonic chip. This is the CAD layout, and then it gets fabricated. So what you see here is an optical micrograph of one of these neurons implemented and superposed on this neural, on top of this neuron that is connected in this neural network. This is essentially a recurrent network that's shown here. So these are your microresonator weight banks for doing the weighting. You have your modulator connected with the photodetectors that's essentially implementing the summing and the nonlinearity. And then we have the electronics on this chip, for example, your capacitors and inductors to get to certain bandwidths. So this is now the actual chip that we have fabricated. We wire bond it with electrical wire bonding, so we can control the currents to each of these modulators and photodetectors and so on and so forth, and provide the biases. But the input and output to this chip is all optical, shown here by what's called grating couplers. So we couple light in and out of the chip. And then to make this usable, we put them on what are called this expanders that then connect them to a PCB carrier. And then we have current sources that we implement on this PCBs. So essentially now what we can do is that program these chips, by interfacing with our software. So we have, for example, TensorFlow or standard machine learning libraries like PyTorch or TensorFlow, which compute the weights, and then those weights can be uploaded onto this chip using this PCBs. And I'll show an example of this. So, so now I'll talk briefly about some of the applications here. So one of the applications that we are very interested in is essentially applying this to a real life world problem, and sort of, trying to recognize digits, trying to recognize between 0 and 9. We wanted to use this in a real world application to see, rather than just a toy-based problem, can we actually use this for something significant? So an area that we were very interested in, and I'm not an optical communications person, but apparently there's a very strong need here. We have a very long fiber link, and the reason we are able to talk right now with Zoom is because we have a fiber optic link that is connecting all of us together. And this is a very long transmission-based system, tens of thousands of kilometers of fiber. And there's optical signals that are transmitted on this fiber. But because these fibers are so long, and even if I talked about that this silicon fibers, or they are that they have very little loss, over time, because of the long distances, they would affect your optical signals that are going through them in a nonlinear way. So they're what's called so you need to compensate for this type of nonlinearities. For example, if I have an optical signal, if I put in a pulse, it might spread out. That's called dispersion. If I put in an optical signal on a particular polarization, right? The optical fiber is not perfect, so it starts rotating on that. It starts rotating. So if I have an X polarization, by the time the light comes out on the other side, it might be Y polarized. So there's again, you need to compensate for the polarization as well. My point here is that you need to compensate for all these nonlinearities using what's being done today is using digital signal processing techniques. And so they use right now today, use this type of chips here. For example, this is a chip that's implemented in 7 nanometer CMOS process, and it does more than 800 trillion operations per second. It's a beast of a chip, and it's used in 200 gigabits per second systems, and also 800 gigabits per second systems. So these are massive chips. But what you need to do here is when we go from the analog domain to the digital domain, you need analog to digital converters. As your speeds are increasing on this transmission systems, it's putting so much constraints on this analog to digital converters. And hence this DSP it's becoming very, very tough to, tough to do. And so there's a fundamental limit at, how fast the systems are going to go. So what our collaborators at NEC Labs in collaboration with Princeton, what they propose is that, we're going to offload some of this DSP and do this type of processing with artificial neural networks. And we're going to compensate for this nonlinearities using artificial neural networks. So what they propose was using a very simple artificial neural network here. This is a 2x8x2 neural network, which I'll just talk about very briefly in just a second. But then you can compensate for this nonlinearities. And what they showed that you can actually outperform standard techniques that are used. So what I mean by that is that this DSP techniques, they use what's called digital backpropagation. This is nothing to do with neural network backpropagation. But what they do is that they take this optical pulse and they solve it. They solve for the nonlinearities by solving what's called the nonlinear Schrodinger equation. And this requires you to do Fourier transforms and inverse Fourier transforms and do this over and over again. It becomes computationally very taxing. And they said, well, we can do this, but using a very simple neural network. And our proposition is that maybe we can use a photonic neural network to alleviate some of this speed constraints if we can work on these optical signals directly. So as a proof of concept, what we did was looking at a very long transmission system, working at 32 gigabaud on a polarization multiplex 16 QAM system. So this is a very high bitrate system, essentially. We trained a neural network, which is a 2x8x2 neural network, and using what's called a regression problem. And we generated a lot of input data, to train this neural network. And I'm not going into the details, I'm skipping over this, but our paper has just been accepted to be published in Nature Electronics. That will be put up on arXiv very, very soon. So I'll be happy to send you a preprint of this paper. But the point here is that, we can train such a neural network, which can then estimate the amount of nonlinearity that you would have on the received data. And then you can subtract that nonlinearity that you have on the received data, and then compensate that way. All right, so that's what's shown here at the bottom. And what we did was implement a layer of this neural network that I showed previously. This is just a 2x8x2 neural network, physically using a silicon photonic chip. And so that's essentially how we train our systems. So, I think someone asked a question earlier, how this system's trained? Well, in this case, it was trained offline. So what we do is that we get the system parameters from this chip. We have the nonlinearity for our modulators, for our neurons. This is a Lorentzian based nonlinearity. We have that as an activation function. We use that as a training parameter with a standard, computer in conjunction with the GPU, and we optimize for the weights. Once we have the weights, we upload them, and this is essentially how the training process happens. And then we see, whether we're able to improve the quality factor of our signals that are coming in. This Q factor essentially is representing how well you've compensated for your symbols. And what we showed here is that, yes, we can actually do this with a very simple neural network, get performance that is equal to, if not better, than the DSP techniques. So once you have got those weights and biases, using this standard machine learning library, we can now take those weights and biases, convert them into appropriate current and voltages, and upload them on this neural network, and then repeat the experiment. And what we showed is that this experimental demonstration gets performance that is equivalent to what you might do numerically, but this is really happening on a much, much faster time scale. Still some areas of improvement, but this is to us one of the first demonstrations of this type of silicon photonic neural networks used in a real-time, real-world application. So again, this paper is soon to appear, and I'll be happy to send a preprint of it. Another area that we looked into, and I'm looking at my clock and I see I'm at the 51-minute mark, so I'll start wrapping up very, very soon. Another area that we looked into was predictive control, where we might, and I'll just show just a highlight of this, where we wanted to intercept a fast-moving object, but we wanted to predict where it's going to be in the future. Now, you can boil this down to what's called a quadratic optimization problem, a quadratic programming problem. And this can be implemented using a neural network. This is something that was proposed by John Hopfield and David Tank, more than 30 years ago, using this type of Hopfield network to solve an optimization problem. And what we showed is that by using optics, we can actually do this on a very, very fast time scale. And very importantly, the number of variables that you increase in the system does not really affect the convergence. So again, this is just a highlight. I'm not going into any details here. The details are in this paper, listed at the bottom. But what we showed is that if you look at state-of-the-art electronic controllers here, this was, I think, an FPGA solving this with the same number of variables. You could do this on a millisecond time scale, while with optics, you could do this 1,000,000 times faster, which is essentially on a nanosecond time scale. And the convergence times here was not affected by the number of neurons or the number of variables that you have. And then lastly, another application that people are interested in is speeding up vector matrix multiplications, as I talked about in the beginning. One area is, of course, in deep learning, where you're doing a lot of this convolution operations, right? You have this weight matrices, essentially these are your filters, these are your kernels, and you're convolving your input image. And then you're using those convolved features to then do the feature extraction. Well, what we see is that for all this type of neural networks, more than 80% of the time is spent in doing this type of convolution operation, essentially doing this vector matrix multiplications. So what we have proposed, and this is in the paper here highlighted at the bottom, that you can now use multiple of these microresonators, just not one a particular weight bank, but you can put multiple of this here, and you can encode your input image that can be encoded on multiple wavelengths using many of these microresonators shown here on the left. And then you can process multiple kernels here. Oops, sorry. You can process multiple kernels here. Oh, I should have shown my laser much earlier. But you can process multiple kernels in parallel. And this is where the advantage of this wavelength multiplexed approach comes in. And you can do this all with a single time step. So you can multiply not only a vector with a matrix, but you can do a dot product of two matrices in a single time step, limited by how fast you can detect this using photodetectors. So a very nice experimental demonstration of this was done by Bhaskar's group earlier this year, where they showed this wavelength multiplexed approaches. They used what are called frequency comb lasers, where they generate multiple of these wavelengths, and then they do this matrix multiplication using what are called phase change materials. And they were able to get impressive performance. This was a paper that was published in Nature earlier this year. Experimental results, so here they're showing that you can take an image and then start applying different types of filters on it, and they're able to get precisions here for 5 bits. So to compare here, there's their photonic tensor core. They were able to achieve, or at least claim to achieve, was around 2 teramax per second. They normalize this per unit area because optical devices are much larger. So this is around 500 gigamax per second per millimeter squared with 5 bits of precision. You compare this with standard electronic, like a Google TPU, for example, the compute densities here are around 150 gigamax per second. So you can see that by using the simple approach, you can potentially speed up the compute densities. Of course, with electronics, you get much higher precisions. And also, what's really not talked about is the energy consumption, which of course, with optics, you're still trying to get there. But the future projections look promising. Of course, there's a lot of work to be done, but what they promise is around 1 petamax per second and teramax per second per millimeter square compute densities. This is all using analog photonics. The question is, how does this compare with analog electronics, right? People are trying to implement neuromorphic hardware using analog electronics, using memristive crossbar arrays, and who wins in the limit? So I'll leave that discussion, to the question answer period. So to wrap up here, this is what our vision looks like, what for a neuromorphic processor, photonic neuromorphic processor might look like as a coprocessor. It will depend on whether the inputs are all optical, right? So I showed an example where the inputs are coming in, where you're processing optical signals. In that case, your inputs and outputs are going to be all optical. But imagine you're processing RF signals. These are wireless signals, then you need to modulate them. Convert those electronics into optics, and for that you need very, very fast modulators. Lots of work happening on trying to get this lithium niobate modulators on a silicon insulator platform, and you need very fast photodetectors. If you want to do digital signal processing, well, you need digital analog converters and analog to digital converters, and you're going to be limited by the speed of such devices. But the point here is that you can do parallel processing using wavelength multiplexing, and potentially can get some speed up in that domain. If you do that, you need frequency comb lasers, to generate multiple wavelengths, and those need to be integrated. And so people are looking at what are called photonic wire bonding technology. Finally, you need memory, which I've not talked about at all in this presentation, but you need tight integration of memory. Do you use digital memory that is volatile, or there are people looking at programmable analog memory? So this is but this is as not as reconfigurable. It is reconfigurable, but you cannot change this very, very fast, and people are trying to do this using phase change materials. Finally, how tightly can you co-integrate the electronics? And will this be monolithically integrated or heterogeneously integrated? So again, we have highlighted a lot of these challenges that would be required, and the advances that would be required. And you can read more about this in our review article that came out a few months ago. So to conclude, or to just wrap up, I think there are 3 areas that have really come together over the last decade. Number one is scalable computing models, people looking at deep learning, spiking networks, and also now new ways of training using equilibrium propagation. It's a paper that came out by Yoshua Bengio I think was it late last year, where you show how you can train this analog-based hardware related to the question that was asked earlier. And you have this, you can do parallel processing with this analog photonics. This is, of course, something that was tried back in the 80s, but the challenge here was integration and nonlinearities. Of course, there's been lots of work on neuromorphic electronics using the silicon industry to create large-scale platforms, but the challenge here is bandwidth. And there's, of course, been a lot of work in trying to program the systems, right? And so, as I mentioned, there's a very nice Nature article that came out late last year. So these three areas have come together, and I believe now is a very good time to start looking at neuromorphic photonics. So, we have this review article, but if you want to get more for historical perspective, we have our book that came out also a few years ago. I realize my order of slides is inverted, but I think in conclusion, I believe that optics is potentially a good platform to get massive number of interconnects. This is all compatible with commercial integration technologies. And we really need to look at tasks and applications where optics might be, where optics can help, right? So we don't want to look at the same applications that electronics is doing, but really look at new applications that it can enable. So thank you very much. If you have any questions, I'll be very happy to answer. And so thank you once again.
So please ask your question directly to Bhavin, or put them in the chat and we can read them. So I have a naive questions to start. Like when you're talking about those photonic foundries, are those the same as people use for electronic signals, or like they're like completely different entities?
Sorry, please come again. I was trying to get my presentation back up.
When you were talking about photonic foundries, like to build those chips, are they the same that the people use for electronics chip, or like they are completely different entities, the foundries to make the chip, the photonic chips?
Oh, I see. Yeah. So so the foundries are, the foundries that I showed, these are silicon photonic foundries. So they are specializing in making this silicon photonic chips. However, there's been lots of work on monolithic integration. So there's, like, for example, global foundries now, where they use the same foundries for making optical components, but also for making electronic components as well. So we haven't yet worked with them, but what I showed was the AMF foundry, for example, does silicon photonics. But yeah, to answer your question, there are foundries that do both as well. Yeah.
Okay.
And that's really the motivation with silicon photonics, because we can now start co-integrating CMOS and electronics on the same platform. So, yeah.
I'm really interested in the scalability question. So great talk. This is very exciting work, and looks very promising for the future of machine learning and AI. But to come back to the scalability issue, is there a theoretical upper limit to all-to-all connected networks using this approach, and also what is the practical limit?
Okay, so very good question. The question is about the scalability. I'm going to share. I'm going to pull up some slides that I can quickly maybe show. This is maybe from a different presentation. But yeah, there is a fundamental limit, So I kind of talked about this all-to-all connected networks, and I said, oh well, you can put multiple neurons here, and so there's obviously a limit, right? So if you look at this, we're weighting the signals, and these are weighted by using this microring resonators. And I mentioned they have a certain free spectral range. So this free spectral range is going to, it basically tells you how many rings can you put one next to another before you start having crosstalk. So if you look at a standard, silicon photonic platform, there's a standard transmission window that you can work with. You're looking at the infrared region of light, so you get around 50 nanometers of light to work with. And so how close you start spacing the channels, really limits on how well you can, how many channels you can have. So for example, you can have around spacing of around 0.8 or 0.4 nanometers. And so by looking at this free spectral range that I talked about and looking at the channel spacing, this number can be roughly around 50 or 60, where you can start getting, you can comfortably put around 50, say, neurons with all-to-all interconnections. Doesn't sound like much, but then we have shown work in where we can minimize this crosstalk and look at some interesting ways in where we can look at what are called coherent effects, which I'm not going to go into the details, but the point that I want to make here is that we can show that this is now around 100 neurons that you can connect. And so there's a fundamental limit on how small you can make the microrings. So I guess what I'm trying to say is that the smaller you make the microrings, the larger the free spectral range. The larger the free spectral range, the larger the end. There's a limit on how small you can make the rings, because you are going to be limited by the diffraction limit of light. You can't make optical components smaller than the diffraction limit of light. So there is a fundamental limit there, as you mentioned, but there's a practical limit, as you also highlighted, and the practical limit here is crosstalk. So by taking both into account, practical limit would be that we can get around 100 neurons together. And the question is, 100 neurons still tells you that you have around 10,000 interconnects, right? This is still relatively large, but how do you go larger than that? So people have looked into what are called hierarchical networks, where you can start having, this is pretty much like the way you use cell phones, right? The way you have certain frequencies and you can reuse those frequencies. The same way we have here frequencies of light that can be reused. So you can imagine that you have a recurrent network that's part of a larger recurrent network, and that's part of a larger recurrent network. And so we're working on that. And so this is one way of scaling these networks up. This is for recurrent networks. But if you think about feed-forward networks, then in that case, what happens is that what people do in optics is that they just implement 1 or 2 layers. That's all. And then you can have 100 layers if you wanted, because they use this in a recurrent fashion, right? They use the same layer over and over again, and they have the flexibility to use the same layer over and over again because of the bandwidth that optics offers. So you have fundamental limits on how many neurons you can put in a given layer, which can be around 100 using our approach. And then you can scale that up using this type of hierarchical networks. But then the number of layers that you can have, that when you kind of, sorry about that. But the number of layers that you can have can be arbitrary based on how fast your system is, right? So I hope that answers your question in terms of not only in terms of the number of neurons per layer, but the number of layers that you can have, which can scale arbitrarily in the number of layers.
Yeah.
I have a question. Early in the talk, you mentioned using current to control the diffraction in these loops that are representing the weights, right? And you were using them as heaters, basically.
That's right.
Is that still the implementation method? If so, where is the current level stored, and how is it fed in?
Thank you for that question. So the question is, of course, how these weights are being controlled, where they are being stored, and I guess what is the limitation. So maybe I'll start off with the limitation. So I notice there's a lot of background. I'm not sure if someone, if everyone is getting that background noise.
It's probably me. I'll turn my fans on.
Okay, no worries. Thank you. But please feel free to unmute yourself and ask questions. So here, what I showed was that we wanted to kind of do, this was just as a we wanted to do a quick and dirty demonstration that yes, we can tune the refractive index by using this heater. And this is okay, if your weights are going to be static, right? And so right now, where the weights are essentially stored, they're kind of stored, they're stored on current sources essentially. They're controlled, or the way we actuate the current sources, which is not really practical. What people are looking into is integrating CMOS-based controllers very close to this silicon photonics platform, where the currents are then where the current is then stored digitally, or on electronic controllers. Having said that, using this way of controlling the current is very slow. It's on a millisecond time scale because you're using heat, right? So what we have been looking into is controlling the currents now using this effect, which I highlighted, where instead of controlling the refractive index using temperature, we can control the refractive index using the number of free carriers that you have. So again, it's now applying a current, but this current is not generating heat or anything. It's just essentially modulating the amount of free carriers that you have within this microring. Of course, this microring now would need to be doped with holes and electrons to get this effect. And so this happens on a picosecond time scale as opposed to a millisecond time scale. So you can now reconfigure this weights much faster than you would be able to do with heat. And again, this again, you need a current again to control this refractive index, but that is stored digitally, very close to this microrings. Having said that, what we have done, what people have shown, and this is again Bhaskar's group, they use what are called phase change memories. So these are optical memories. So rather than storing this currents digitally, what they do is that they change the refractive index here of this material using what's called this phase change material. So they put in a bit of current in them, and that permanently changes the properties of this material. They go from an amorphous state to a crystalline state, and you can tame the properties of this material, and this is kind of set in stone. So you put in a high optical power, or you put in a bit of current, and that changes the refractive index. And so that is essentially what they call an analog optical memory. So that's another way of doing it. So I hope that answers your question. I know a long answer, but
yes. No, thank you. Yeah, that I get it now. Thank you.
Yeah. Thank you again for that question. It's very, very insightful. Any other questions that I can help answer?
I had a related question, which was, do you have to do kind of any compensation for thermal crosstalk between the heaters to get that 5 bits resolution right now?
Yes, very good question. Yes, we have to compensate for the crosstalk. This is using what are called feedback control methods. I'll show a slide here that was hidden, which I did not present, but maybe now a good time to present. So what we do here is, so when I talk about that we have a heater, we actually don't put a metal on top of that was what we did initially, but we have another way of doing this. These are what are called in-resonator photoconductive heaters. What that means is that, a fancy term, but all that it means that we dope the silicon, this piece of silicon that you see here, by an N-type material, and we dope it, lightly. This essentially makes this essentially creates a lot of charge carriers. The point here is that as your optical light or optical mode, which is your light that is circulating in this ring resonator, it's going to generate free carriers, right? When it generates free carriers, it's going to decrease the conduction. It's going to increase the conduction and hence decrease the resistance. So what we do is apply a current here and measure the change in resistance. And this we can do with a large scale network. So people have shown this, you can do hundreds of such devices. The point is that when we measure the change in resistance here, we can see that when there's light in this waveguides here, it's going to create this dip in this resistance, and we can monitor this peak. And by monitoring this peak, if the temperature changes in the environment, then this peak is going to start moving. And so we have a feedback algorithm that says, okay, if I'm at this particular current and this is the resistance, can I move it back? And so this happens in real time, and it starts controlling this. And with this type of control method, so we have a couple of papers that came out here. One of the latest ones was in APL Photonics that describes this method, and it compensates for this. It compensates for this crosstalk in real time. The thermal crosstalk, the electric crosstalk, and the optical crosstalk, all of those. Because you can imagine if in multiple rings, you'll not only have optical crosstalk, but you'll have some heat that is generated in one ring, in effect, another ring that, the nearest neighbors. And so we were able to get around, with this method, we were able to get around 7 bits of precision. And very recently, I don't have the paper listed here, but we have a paper on arXiv that now shows that we can get around 9 bits of precision. So there's a trade-off, how fast can you compensate for this feedback, and what the bit precision that you can get here. So that will again depend on the applications, how fast you want to reconfigure the weights. If you're doing simple convolution-based operations where in deep learning networks so the weights are kind of set, then this is a potential method of getting higher bit precisions. But in areas where you want to keep updating the weights, then the bit precision is going to go down because you need to update the weights very fast. So again, I know it's a long answer to your question, but yes, you can do this. You can do this in hardware, and people have shown, our collaborators, in fact, they showed, and I think I have a slide that shows it right here. They did this with. This is the one here. This is the paper at the bottom. They did this with 16 by 16 micron resonators. So, so more than 250 of these ring resonators being controlled with this technique as well.
That's really fascinating. Thanks.
Thank you for that question. Any other questions that I can help answer? I know this is a lot of material, and I do appreciate you being very patient and me explaining this from from assuming with very background. Yeah.
I have a quick question. I know that this is still in the experimental phase, but do you have any idea on cost comparison? With the silicon processing versus silicon processing.
Sorry, to understand the question a bit better, you mentioned the cost. Sorry, are you talking about sort of the manufacturing costs?
The manufacturing cost, the implementation cost, if it was actually going to be used in a practical way, yeah. Is it actually, because I mean, it's there's a lot of exotic stuff in here. And the question is, although I realize it's using existing manufacturing processes, but would it actually be cheaper than our normal digital processing, which is still progressing?
So that's a very good question. I do agree that we have to be cognizant and think about that, and usually as academics we kind of don't think about at least I have not at times thought about this, but to answer your question, silicon photonics has become quite mature. people have used silicon photonics now in data centers, so people are actually making this large scale photonic integrated circuits using silicon photonics. It's all foundry compatible. And I don't know the exact cost, but this is now a few cents, that you can make some of this type of devices, per chip. And this already has application. People have used this in, I think a lot of data centers already using this silicon photonic chips now for transmitting data between different racks or servers. So that is a reality. Now, but the question I think is deeper, because it's asking now, where, well, you have this new materials, you have things like phase change memories, you have people using materials like graphene that I've not talked about, but we have graphene based modulators. People are using ITO and other type of exotic materials. That is not foundry compatible. And so, I don't know the cost, that would be associated with that. It's not foundry compatible. We do that post processing in our clean room. So even if all these chips are fabricated in foundry processes using multi-project wafer runs, we still have to do some of the post processing later on. If you want to deposit graphene, we want to deposit other types of materials like phase change memories. And so I don't know the cost that's going to be associated with that. I'm thinking that it's going to be expensive because it's not standard. But I think if there is an application, where there is maybe there might be a cost benefit scenario, right? So I'm sorry, I really don't have a good answer to your question, but.
Okay, well, I didn't expect a real good answer, because I mean, you're still, and we're talking very general, here, but it just brings that up. But I do think the power saving is a really interesting aspect of it.
That's right, and I think that's really also driven by applications. I know people are interested in autonomous vehicles where they want to do edge processing, right? So they're, if you say that my hardware accelerator is going to use 100 watts of power, they don't want to use that in a car where you need to have a big power source, that you're carrying in the car, right? So there is a lot of interest, though we have not done any work on that. There's a lot of interest in doing edge-based processing where you're processing a lot of data in real time, massive amounts of data. The post-processing can be done once you've done the dimension height reduction, once you have done the heavy-duty lifting with even if with low precision. Later on, it can be done with electronics with much higher precision and more fancy, more fancy based algorithms later on. But the initial kind of the grunt work is where optics might be helpful, which can help reduce a lot of that power consumption in the beginning. So I agree with you that if there is a very strong application, very strong need, for example, in autonomous vehicles, then we would just bite the bullet and say, okay, we'll pay whatever cost that is associated with manufacturing this, knowing that it's going to save a lot of power consumption, for a given application. So I agree with you. Yeah.
Thank you.
Thank you so much for this. Yeah.
Oh, I'm sorry. I wondered if you had thought at all about learning rules that could be implemented in the photonic hardware part rather than using CPU and GPU, and whether there might be learning rules that would be better adapted to this approach that were not efficient in a von Neumann architecture, but would be efficient here.
That's again a very insightful question. Thank you for asking that. Yes, currently we've been training our systems offline. So even if we claim that, we're using this photonic hardware and hey, check, it's really fast and it can do these applications, they're still trained offline, and the training process takes a really long time, right? So having said that, we have looked into hardware-based training approaches. One of them, I think that is, and this really comes with a lot of innovations from the machine learning community. Recently, there's been work, as I mentioned, by Yoshua Bengio on what's called equilibrium propagation, where they proposed that you can use the physics of your hardware and implement optimization problems directly, with the hardware, and use that as a training platform. And this can train analog hardware in real time. This is called equilibrium propagation. So we've been looking into that, how we can do equilibrium propagation with our photonic-based systems. We have a paper that's going to be put on archive very soon. This is using what's called direct feedback alignment. So, these are methods which is closely related to backpropagation, but it's more conducive for hardware. And so, again, in that case, it's a different type of learning method, which I'm not going to go into the details right now, but it's more conducive for photonic-based hardware, and we think that might be one approach for doing training in real time. And finally, there are people looking at dynamical learning methods, right? So, they are coming up with new type of training algorithms that can be more tied with the physics of the particular hardware. And so it's not only backpropagation. Backpropagation was essentially invented because we wanted to be able to use it on a von Neumann-based architecture, which is not really, as you mentioned, not really efficient. And so, I don't have any slides right now. This is all work in progress, but we will have a paper that will hopefully be put on an archive, once my student implements our edits soon. And I think there's a lot of work going on by others as well. I know, for example, there's work going on by Lighton, the company that I showed that was that has a product in Europe. They are also implementing this direct feedback alignment in their hardware. And I remember seeing a talk at NeurIPS last year by that group, by Sylvain Guigon. So yeah, so there is work. I don't think it's there yet, but there is work. It's not yet mainstream. Yeah. So very good question. Any other questions?
We have time for one last question, so please don't hesitate.
I have one question. Nice talk. Thank you very much for your talk. My question is related with the micro ring. When you change the temperature, there are two effects. One is introduce nonlinearities, and they change the index. They have a reflection in that case, and that increase crosstalk. How you reduce the crosstalk? Because you have two waveguides in this time. Because when you change one part of the waveguide, the index, you have increased the reflection in the waveguide, and then increase the crosstalk. How it changes the resonance of the ring? How you control this part?
Okay, so that's a good question. The way we do that is, each ring is pretty much independent of the other ring. The time they start interacting with one another is because you might have some thermal effects. For example, if you're using any type of thermoptic effects, you'd have some type of thermal crosstalk. But I think you're also asking here about the optical crosstalk. So what we end up doing, and I think this is your question, right? Let me see if I can just share my screen, and I think that is very insightful. Let me see if I actually let me just get to that slide, because I think this is very, very important, that what you just mentioned. Yeah, so let me just share now my screen again. Hopefully
you're already sharing.
Oh, I'm sharing my screen. Okay. Yeah. So here, how do I minimize? Yeah. So here you can see that, the question being asked was this, right? And maybe it's easier for me to draw, is that I have one ring here and I have another ring here. And so what would happen if I am now changing this ring such that happens, right? So there's this amount of crosstalk. So if I'm weighting the signal here, I will also start weighting another signal that's here. So there's that. Yeah.
Before, because it's in the same ring. Because when you change the temperature in one part of the ring, then you divide the ring into parts, and then the resonance change in that time.
Sorry, let me understand your question better. So you're saying that if I'm
and you change the temperature, and when you change the temperature of one part of waveguide, and that part introduce nonlinearities in this part of the waveguide, and then reflections. And then that reflection leave from the ring. And then the question is, increase the crosstalk between the rings, and then introduce more noise into the signal. I don't know how you control this part, is my question.
I see. So I think one thing that I should clarify is that, when we are heating a very small part of the ring, this is actually not the full representation. So typically what we would do, and I think I did not present this slide, but it's actually the whole ring itself that we're heating up, right? It's this is just an illustration saying that, of course, if you were to put a metal heater, you can locally affect the refractive index, but for more precise control, you're right. We actually deposit it on the, pretty much on a large part of the ring. So this was where we had metal heaters that were deposited, but as you can see, in this case, it's the whole ring itself that acts like a heater, right? So the refractive index is changing everywhere uniformly at the same time, right? So it's but having said that, I mean, I guess your other question is, I don't know if I understood this. Yeah, sorry, come again.
Sorry, the nonlinearity of this effect. That when you change the temperature, they introduce nonlinearity in the waveguide, right?
That's right. Yes. So yeah. So again, I have skipped over those details, but what happens is that this process, once you apply a current, and then there is power dissipation across this metal, whether you have a metal heater on top or you're using this type of N-doped material, within the ring, you'll have power drop across it, which changes the temperature, which changes the refractive index. That process itself is very nonlinear. So what we have to do is that if a user wants a certain weight, right, we need to figure out kind of backwards what the current value should be. So it's not a one-to-one mapping. You're right, and so there's it's a highly nonlinear process, and so here and here is, that's why I did not of course I did not mention this, but if you see what's happening here is that I'm generating these points. You will see that it's only a certain region here that the quantization here is kind of linear, right? So it's a highly nonlinear process, but you can linearize it in this region here. So depending on what the quality factor of your ring is, so how sharp or how wide your ring is, it will really affect how linearly you can read out these weights. So again, just to recap, if you want to have a certain weight value here, this will essentially give me a certain weight value W. You need to find out the mapping between this current here and this weight here. And so you would have this weight that you would want to put in, that's your weight that is, that is expected, that will map onto a current, using some calibration process, which I did not talk about. But then you'll get an actual weight here. And so we typically, what we plot is the weight expected versus the weight actual, and that hopefully should be a unity line, through 0, 0. And we can only do that well enough if we are in this linear part, where we're changing the temperature, right? Or where we're changing the current. So you're absolutely right that, because of this nonlinear process, well, how do we compensate for it? We don't really compensate for it. All we just do is that we try to work in this linear region, and do the weighting there. So instead of saying the weight will be 0 here and 1 here, we kind of renormalize this and say the weight will be 1 here and the weight will be 0 here. Right? So yeah. So again, I know this is going a bit into the details and a bit into the weeds, but I think necessary to answer your question.
Thank you very much. I appreciate your talk. Thank you.
Yeah. No, thank you.
Well, thank you again, Bhavin. It was a really nice and interesting talk.
Thank you very much. Thanks to you and to Gert and everyone else at INC for having me today. And I'll be happy again. I'm happy to chat, one-on-one, and we're always looking forward for collaborating and so on and so forth. So especially with people doing electronics. So if you have any ideas, I'd be very interested in talking in more details about how we could work together. So please let me know.
Yeah, hopefully, like some good constructive collaboration might just start from the talk, and collaboration with Gert's group, perhaps.
No, thank you once again. Yeah.
Thank you.
So, yeah, thank you for organizing this.
Thank you. Astounding work, really.
Very interesting. Thanks a lot.
Thank you so much. Thanks. Yeah.
All right, so I will stop the recording.
Yeah.
Thanks.
Perfect. Thanks.